Welcome to our hyperbolic geometry video in which we're going to do the hyperbolic center of a hyperbolic circle. And I got to hide this real quick. Good. So what we have is the hyperbolic space, that's this circle right here. Let's construct the interior just so you can see. That's hyperbolic space, everybody. That's hyperbolic space, just this. So this is a circle. This is circle E, but that's a funny name for the circle. Can you tell me why that's a funny name for the circle? We can call it circle E, but why is that a funny name?
It's a hyperbolic circle.
And that's the Euclidean point. Yes,
Yep, yeah.
That's the Euclidean center E, and that's a good name for it, E for Euclidean center. But it's funny to be in hyperbolic space and to be calling it by its Euclidean name.
Yeah.
So let us find its Euclidean center. So one of the things I've done is I've done the construction for a hyperbolic line, that's this red thing here, hyperbolic line that is perpendicular to both the circle E and the boundary circle. Well, to be perpendicular to the boundary circle is what makes this a hyperbolic line. But to be perpendicular to E gives it the following property. I have a line perpendicular to a circle. Therefore, it must go through the center of the circle. Even in hyperbolic space, that property shows. So here's what's going on. Let's watch. And if Miss Penn would point to the hyperbolic center.
Right here.
Yep, that point doesn't move. Isn't that interesting? This point right there doesn't move. Even as point P rides around the circle, and we have all these different hyperbolic lines. All those hyperbolic lines perpendicular to both the boundary and circle E, that's the hyperbolic center. Isn't that cool? So let's label that hyperbolic center. And what do we call it? What do we call the hyperbolic center?
H.
H is right. It's a good name. So that's what we're going to be calling these things all the time. Is we'll call the well, I better let's do it this way. I know what to do. So E for Euclidean center, H for hyperbolic center. So that's what's going on. This H doesn't move as long as this circle doesn't move. But if I play around with this circle, if I move this circle, if I change its shape, if I bring it closer to the boundary, H gets closer to the boundary. If I move this circle further from the boundary, H gets further from the boundary. But E is always closer to O than H is. And that's because of the hyperbolic distance formula. Like right now, let's get a little bit better looking spot. Right now, this distance from H to here, that's a hyperbolic radius. And from H to, is that an F? That's a P.
P, yeah.
H to P is a hyperbolic radius. So here's a hyperbolic diameter, and the hyperbolic distance of that segment, that arch, that's a Euclidean arc, but it's a hyperbolic segment, is the same as this. These are both diameters. I know they don't look the same in Euclidean value, but that's how they go. Well, let's see how to perform this construction. So it's as if we were given just the circle. Let's temporarily make this line really thin. I'm going to make a hairline style thin. All right, so we're given this circle inside of this space. Well, we must have its Euclidean center. So we don't know H yet, but we do know E. So we make OE. That's the first thing you do. I mean, when you see this problem starting out, all you have is a circle inside of a circle with their centers. You make that ray, OE. Then you construct a hyperbolic line. You pick point P anywhere. And here is the construction of P inverse. I made OP, and it's this long ray. Then I did the perpendicular to P. Then the radius to that point. And then the perpendicular there. And that point right there, that is P inverse. That's the inverse of point P. And let's observe some properties about the inverse of point P. As P gets close to the boundary, P inverse gets close to the boundary. As P gets close to O, P inverse gets further away. Let's watch and see what happens to P inverse. Look at P and P inverse get close together and then get further away. And now they're getting close together again. P and P inverse getting close together. And then P's getting close to O, P inverse gets further away. Now there's a little bit of interesting math going on here. This dude right here, this thing I'm highlighting, that is the perpendicular bisector of P inverse. People who want to get an A in hyperbolic geometry have to understand the use of this Euclidean line. It stands for a very long sentence that I'm going to lay on you now. Any hyperbolic line through P has its Euclidean center on this line. So if I want to make Euclidean, if I want to make a hyperbolic line through P, I'm going to use that. I'm going to use the perpendicular bisector of a point and its inverse. It takes a few steps to find it, but it is so worth it. It's very rich. I can use it for a lot of things. In this case, I used it with the tangent at P. Here's the tangent. I go from Euclidean center now. See, I want the Euclidean tangent. Euclidean tangent happens to be the same as hyperbolic tangent. But, well, this is not a hyperbolic line, but this tangent I want, because then if you look right here, the angle that this hyperbolic line makes, which I will now make nice and big, the hyperbolic line makes a right angle with this green circle because I made it that way. So how did I do it? I got the perpendicular bisector of PP inverse to intersect with the tangent. So what two properties am I combining? I'm combining the center that's going to give me a hyperbolic line with the line tangent that's going to give me the right angle. So I'm getting a hyperbolic line that is perpendicular. I'm combining the both Euclidean properties to get the hyperbolic object that has the properties that I want. So as a Euclidean object, these two circles are orthogonal. As hyperbolic objects, I have a hyperbolic circle perpendicular to a hyperbolic line, which means this red guy must contain the hyperbolic center. But this straight guy is also a hyperbolic line. And it's a hyperbolic line perpendicular to this green circle. So it must contain the hyperbolic center. So the intersection of the straight with the curvy gives me the hyperbolic center. And one more time with the animation, just to show that point H does not move. That's the center. All these diameters are spinning around this circle. All these diameters are spinning around and they pivot at H because it's the hyperbolic center. All right, one more cartoon. Oh, it's not a cartoon. This one's the other animal here. And now I've given myself a hyperbolic line. Do you see it with the Euclidean center D?
Yep.
So here's our space O. And I'm going to do the midpoint of the segment CB. Everybody ready?
Yeah.
All right, what do we do first? This segment, Euclidean segment, Euclidean perpendicular. Construct. Again, this segment, perpendicular, construct. Where they intersect, I want to have a point marking that because I'm about to do a ray. Let me get that point of intersection. The ray from O to that point is going to contain the midpoint. So believe it or not, this guy right there, that is the hyperbolic midpoint. Let me mark it with an M. That guy, M, right there. Let me emphasize, I'm going to change his color. Make him yellow. That's the hyperbolic midpoint of the hyperbolic segment CB. I'm going to hide all the straight stuff temporarily. I don't even need those. But I'm going to bring them back, so I'm going to make an action button for hide show. All right, good. Hide them. Okay, so now, well, this point's an important point later, but for now, check it out. This guy M is the midpoint of the segment CB. Now it looks like MC is a slightly shorter arc than MB, and it is, because C is closer to the boundary. Now I can drag C, and look at that. That midpoint follows after C like a little dog. And as C gets really close to the boundary, the midpoint gets really close and actually disappears from sight as I hit the boundary. So look at that. And now let's suppose C comes over here, and now B goes toward the boundary. The midpoint follows B. So this distance, MB, same hyperbolic distance as MC. And it's because of the hyperbolic distance formula. Hyperbolic distance formula counts a little bit toward the boundary, counts as a lot more than a little bit away from the boundary. Now let's see, why would this construction, which seemed to be fairly simple, why would this construction actually be true? And it goes back to what we were talking about. I'm going to draw one circle. And it's going to have its center right there. And I'm going to make it green because it's not a hyperbolic line. I'm going to just make it look nice and bright green. That circle is not part of the construction, but check it out. This point here, I'm going to call it E, because it's the Euclidean center of Mr. Green's circle. You can see it. EB is the same size as EC. So those are radii. And now, here's a hyperbolic line that contains E, and it's perpendicular to the green circle. So this must contain, this guy right here, this ray, must contain the hyperbolic center. And here is a hyperbolic line. Didn't we make right angles here? Yes, we did. Here's a hyperbolic line that is perpendicular to the green circle. So this guy that I called M is the hyperbolic center of the green circle, undrawn. So if that's the center of the circle, then this is a diameter, and that's the midpoint of the diameter that makes it the hyperbolic center. So it's interesting that the same idea gets used twice. In the book, these two ideas are next to each other.
Gives you the most bang for your buck.
Well, a lot of, yeah. So what is McDaniel going to ask a bunch of questions about in week 2 and in week 1? Week 1, you're talking about the identity of, like, this is a drawing. This is the first drawing on the first hyperbolic wiki. And I'm asking about hyperbolic segment MC. What is it in Euclidean talk? Oh, it's just the arc of circle D beginning at M and ending at C. It's the arc of a Euclidean circle, but it's also a hyperbolic segment. What is BC? Well, it's a Euclidean arc of circle D. It's also a hyperbolic diameter of circle M, or in this case we would call it H, because, well, whatever the name of this green circle is. So if you call this green circle circle E, I wouldn't mark you wrong, but it's kind of funny. It's like in Spanish class when instead of calling you Senorita Jana, they call you Mrs. Senior. Oh God. Well, see, let me try it again. Instead of calling me El Profesor Miguel, they call me El Profesor Mike. What'd you do that for? You know, so you've got the Euclidean name, the hyperbolic name of the center. So that's interesting. If you can keep that sorted out, that's really, really good. So go back to that wiki and start naming stuff. But you have to name Euclidean things using Euclidean words, name hyperbolic things using hyperbolic words, and each thing has both names. Each object in this picture has a Euclidean name and a hyperbolic name. Okay? Any questions?
No.
Thanks, everybody. Let's turn off the recording.